It begins not with a sound, but with a silence so profound it stretches across trillions of miles, a silence that has endured for millions, perhaps billions of years, as it journeyed through the desolate, frozen expanse between the stars. And then it enters our home, a trespasser from an unknown shore, an emissary from a sun that is not our own, crossing the invisible frontier of our solar system. We call it 3I, Atlas, the third confirmed interstellar object in human history. A designation that sounds clinical procedural, yet it represents one of the most astonishing arrivals of the modern age. It is a ghost from the void, a fragment of another world, and it has brought with it a mystery that threatens to unravel everything we thought we knew about the fundamental forces that shape the cosmos. Because as this silent traveller falls toward our sun, it does something that should be impossible. It begins to glow. Not with the familiar streaming plume of a comet's tail pushed back by the solar wind like a banner in a gale. No, this is something else entirely. Something deeply, fundamentally wrong. 3I, Atlas, produces a soft, ethereal luminescence that stretches defiantly towards times the very star it should be fleeing. A sunward glow. A celestial paradox that has ignited a firestorm of debate and discovery, forcing us to ask a terrifying and exhilarating question. What have we truly welcomed into our solar system? For nearly all of human history, we have lived with a comforting certainty. We believed we were cosmically alone, not necessarily in life, but in matter. Our solar system was a walled garden, a self-contained island universe, where everything we could see, every planet, moon, asteroid, and comet, was born from the same spinning nebula of primordial dust and gas as our own Earth. They were our siblings fashioned from the same cosmic clay. Comets, those celestial snowballs of ice and rock, were part of the family, distant cousins from the cold, dark suburbs of the Oort cloud or the Kuiper belt, occasionally swinging in for a fiery visit before returning to the familiar darkness. Their behavior, while spectacular, was predictable. As they neared the sun, its heat would vaporize their icy surfaces, a process called sublimation. This released gas and dust would then be caught by the unceasing pressure of solar radiation and the solar wind, a constant stream of charged particles flowing from our star. The result was always the same, a magnificent tail, or sometimes two, pointing directly and obediently away from the sunday. It was a law as fundamental as gravity, a cosmic windsock showing the direction of the stellar gale. There was no other way. There could be no other way. This certainty was the bedrock of planetary science for centuries. Then, in 2017, the first crack appeared in that foundation, an object impossibly fast and on a trajectory that could not have originated from within our system, shot through our cosmic neighborhood. It was named Oumuamua Hawaiian for Scout. It was small, dark, cigar-shaped, and it tumbled end over end like a discarded shard of cosmic shrapnel. Most bizarrely, it accelerated away from the sun with no visible tail, defying our models of cometary outgassing. It was a riddle that came and went in a flash, leaving behind more questions than answers. Was it a new type of comet? An alien probe? We would never know for sure. 2 years later, a second visitor arrived, 2I, Borisov. This one was a relief. It looked and acted exactly as an interstellar comet should. It had a vast diffuse coma and a beautiful tail that streamed away from the sun, perfectly obeying the laws of physics. Borisov was the confirmation we needed, proof that other solar systems build comets just like ours. The universe, it seemed, was not so strange after all. Oumuamua was the anomaly, Borisov was the rule. We had a baseline, we had a theory, we had our confidence back. And then the telescopes of the Asteroid Terrestrial Impact Last Alert System, perched on the volcanic slopes of Hawaii, captured a faint smudge of light moving against the stellar background. The discovery was almost mundane, a testament to the tireless automated eyes we have built to scan the heavens. An algorithm flagged a new object, its position logged, its brightness measured, but when the astronomers plotted its path, a jolt of electricity shot through the global community. The numbers didn't lie. The orbit was not a gentle ellipse tethered to our sun's gravity. It was a steep, aggressive hyperbola, a clear mathematical signature of an object arriving from interstellar space. This was the third one. 3I, Atlas. Excitement was immediate and palpable. Here was another chance, another precious sample from a faraway star system delivered directly to our doorstep. Telescopes across the globe and in orbit above it swiveled to stare at this new guest. The initial observations were promising. It was larger than Oumuamua, brighter, and it was already showing signs of activity far from the Sun, suggesting it was rich in volatile ices. It looked like it would be a spectacular interstellar comet, perhaps even more magnificent than Borisov. Scientists prepared for a cascade of data that would enrich our understanding of how other star systems form and evolve. They expected to confirm their theories. They expected another Borisov. They were wrong. As 3I, Atlas, drew closer, moving from the frigid domain of Jupiter towards the orbit of Mars, something utterly baffling began to emerge from the data. At first, it was dismissed as an artifact, a trick of the light, a miscalibration in the sensitive instruments. Astronomers saw the familiar faint halo of a developing coma, the cloud of gas and dust sublimating from its nucleus. And they saw the beginnings of a tail, but it was pointing the wrong way. It wasn't just slightly off axis. It wasn't subtly curved by magnetic fields. It was aimed with impossible precision in the opposite direction of where it should be. It was pointed towards the Sunday. Imagine standing in a hurricane, holding a long silk ribbon and watching it stream directly into the wind. Imagine a ship's wake forming in front of the bow instead of behind it. This is the level of physical absurdity that astronomers were now confronting. The sunward glow of 3I, Atlas, was not a tail in any conventional sense. It was a luminous, ethereal appendage, a soft spear of light that seemed to be fighting against the torrent of solar energy, reaching back toward the very source of the power that should have been blasting it into deep space. This single observation invalidated our most fundamental models of cometary physics. The two forces that create tails, solar radiation pressure and the solar wind, are relentless and unidirectional. They emanate from the sun and push everything outward. There is no known force, no conceivable mechanism associated with a simple comet that could overcome this stellar onslaught and project material times into times it. It was like watching gravity work in reverse. The scientific community scrambled for an explanation, their initial excitement twisting into a profound sense of confusion. The first hypothesis was that we were seeing a unique perspective effect, an optical illusion created by our viewing angle from Earth. Perhaps a fan-shaped tail which we were seeing edge on created the false impression of a sunward spike. But as Earth and Atlas continued on their separate orbits, our vantage point shifted and the illusion should have resolved itself. It didn't. The sunward glow remained a persistent and undeniable feature. It was real. The next theories grew more exotic. Could the object be rotating in such a way that a single powerful jet of material was coincidentally and temporarily aimed at the sun? This would require an incredible coincidence of alignment and a jet mechanism far more powerful and focused than anything we've ever witnessed. As days turned into weeks, the jet would have to rotate out of view, but the glow persisted, steady and unwavering. The feature itself was unlike any known cometary structure. A typical dust tail made of larger particles is gently curved and yellowish, reflecting sunlight. An ion tail composed of charged gas is straighter, thinner, and often glows with a ghostly blue light as it's buffeted by the solar wind's magnetic fields. The sunward glow of 3I, Atlas, was different. Spectroscopic analysis revealed it was composed primarily of fine-grained dust, but it wasn't behaving like dust. It was too cohesive, too directed. It was less like a cloud and more like a beam. Its light was diffuse, yet it had a defined structure, a tapering column that seemed to emanate from the nucleus and terminate miles out in the interplanetary vacuum, defying the very physics that should have dispersed it in microseconds. Scientists began to question their instruments, their models, their sanity. Every check, every recalibration, every peer review came back with the same impossible conclusion. An object from another star was sailing through our solar system, projecting a plume of material directly into the face of a 1,000,000-mile-per-hour solar gale. The implications were staggering, branching out into a forest of radical possibilities, each more unsettling than the last. Could 3I, Atlas, be composed of materials completely unknown to us, with properties that defy our understanding of chemistry and physics? Perhaps a substance that, when energized by sunlight, is not pushed away but is somehow drawn toward it, a form of negative light pressure. Such a concept exists only in the deepest realms of theoretical physics, with no experimental evidence to support it. To find it embodied in a visiting comet would be like finding a unicorn grazing in your backyard. It would rewrite the textbooks. Others posited even more complex scenarios. Could the object be generating a powerful localized magnetic field, a magnetic bubble that was trapping and funneling charged dust particles into a sunward stream, creating a kind of magnetic antitail? This would require 3I, Atlas, to have an internal dynamo, a liquid metallic core like a planet, something utterly unheard of for a small icy body. It would mean this wasn't a comet at all, but something far more complex, a new class of celestial object entirely, a wanderer with a dynamic planetary-style interior, somehow forged in another solar system and ejected into the interstellar void. The energy requirements to sustain such a magnetic field against the solar wind would be immense, far beyond what a passive frozen nucleus could generate. The debate raged in online forums, in academic preprint archives, and in frantic video conferences connecting observatories from Chile to Arizona. Every new image, every fresh spectrum of data only deepened the mystery. The glow wasn't a fluke, it was the object's defining characteristic. While the far side of the nucleus produced a faint conventional tail pointing away from the sun, this bizarre sunward projection was the dominant feature, brighter and more structured. It was as if the object had a dual nature, one side obeying the laws of physics as we know them, the other side adhering to a set of rules we have yet to imagine. The existence of this faint normal tail only made the sunward glow more inexplicable. It proved that the solar wind and radiation pressure were present and acting as expected. The comet was feeling the push, and yet simultaneously it was exhibiting a pull or a counterforce of inexplicable origin. It was a contradiction made manifest in ice and dust, playing out on a cosmic stage right before our eyes. This object is no longer just a scientific curiosity. It has become a profound philosophical challenge. For centuries we have looked to the heavens and found order, predictability, a universe governed by elegant and universal laws. Newton's gravity, Maxwell's electromagnetism, Einstein's relativity, they described a cosmos that was complex but ultimately knowable. 3I, Atlas, threatens that comfort. It suggests that our walled garden may not just be open to visitors, but that those visitors may play by an entirely different rulebook. It whispers that there are forces, materials, and phenomena in the wider galaxy that are not accounted for in our neat equations. Oumuamua was a strange shape. This is a strange behavior. This is a direct challenge to the physics of our own backyard. It is an active, ongoing event that defies explanation in real time. We are no longer just astronomers. We are cosmic detectives, presented with a celestial enigma that has travelled for eons to confound us. The implications ripple outward, touching upon the most fundamental questions we can ask. What processes in other solar systems could create such an object? Is this a common phenomenon in the galaxy, and we have simply been blind to it? Or is 3I Atlas unique, a one in a trillion cosmic freak? And as the object continues its journey, its sunward glow, a constant silent accusation against our limited understanding, a more radical, more unsettling possibility begins to surface in the hushed corners of the scientific community. A possibility so profound it is rarely spoken aloud for fear of ridicule, but in the face of a phenomenon that breaks the known laws of nature, all possibilities, no matter how extraordinary, must be considered. Is this glow a natural phenomenon at all, or are we seeing something else? A signature of something not just unknown, but perhaps unknowable. A technology so advanced it is indistinguishable from magic. The scout, Oumuamua, was silent and inert. This new visitor, 3I, Atlas, is active. It is broadcasting its strangeness, its defiance of physics in a language of light and dust that we are struggling desperately to comprehend. And as we gather more data, we are beginning to realize that its sunward glow may not be a feature of the object itself, but rather a consequence of its journey. a clue that points not to its composition but to its origin and perhaps its purpose. The story of 3I, Atlas, is no longer just about a curious comet. It has become a search for a new law of physics, a hunt for a new kind of matter, or a reckoning with the stunning possibility that we are witnessing the first unambiguous evidence of something truly and intelligently alien. The mystery is just beginning. And to solve it, we must follow this impossible light, even if it leads us into a darkness of understanding we never knew existed. For nearly all of human history, our solar system felt like a sealed room. We knew its inhabitants intimately, the stoic gas giants, the rocky inner worlds, and the swarms of comets and asteroids. Our celestial family, all born from the same swirling cloud of primordial dust and gas 4.5 billion years. They were ours. Their orbits, their chemistries, their stories were all chapters in the same grand autobiography of our sun. Any visitor we ever encountered, from the brilliant spectacle of Halley's Comet to the silent threat of a near-Earth asteroid, was a distant cousin returning home, a wanderer on a long looping path, but ultimately bound by the same gravitational anchor as us. The space between the stars, the vast silent ocean of the interstellar medium, was just that, an abyss from which nothing ever emerged. We would send our own messages out, encoded on golden records and beamed into the void, but we never truly expected a reply to wash up on our shores. We believed, cosmically alone, our system, an island universe in a sea of impenetrable distance. Then on a crisp Hawaiian night in October of 2017, that comforting illusion was shattered forever. The culprit was a machine, a robotic eye tirelessly scanning the heavens. The Panoramic Survey Telescope and Rapid Response System, or PanSTARRS-1, wasn't looking for visitors. Its nightly vigil was a planetary defense mission, a hunt for rocks from our own cosmic backyard that might pose a threat to Earth. But on that night, it flagged a faint, unassuming speck of light. In astronomy, new specks appear constantly. It's the nature of the work. Yet this one was different. When astronomers traced its path backward, a sense of profound disbelief rippled through the global community. The object wasn't in a closed elliptical orbit tethered to our sun. Its trajectory was a wild, unrestrained slash across the fabric of our solar system, a hyperbolic arc. You must understand what this means. An object on a hyperbolic path is not a member of our family. It is a tourist, and it is moving so blindingly fast that the sun's immense gravitational pull is little more than a gentle curve in its road. It was already on its way out, a fleeting guest who had swung past our star and was now heading back into the abyss. It had come from another star. They named it 1I, Oumuamua, a Hawaiian word meaning scout or a messenger from afar arriving first. And the name was profoundly fitting, for this first messenger was one of the most enigmatic objects we have ever witnessed. As our telescopes strained to get a better look at this impossibly faint traveller, the mystery only deepened. Based on the way its light flickered, tumbling end over end every 7 or 8 hours, it had a bizarre, unnatural shape. It was either an impossibly elongated cigar, 10 times longer than it was wide, or perhaps an extraordinarily thin, flat pancake of a rock. Nothing in our solar system looked like it. It was a piece of cosmic driftwood sculpted by forces and in an environment entirely alien to our own. But its shape was only the beginning of the puzzle. As Oumuamua receded from the sun, astronomers tracking its escape noticed something that defied the laws of physics as we knew them. It was accelerating. It was pushing away from the sun faster than gravity alone could explain. This phenomenon, this non-gravitational acceleration, is not entirely unheard of. We see it in comets all the time. As a comet approaches a star, its icy surface heats up and sublimates, turning directly from solid to gas. This process creates jets of gas and dust that act like tiny rocket thrusters, giving the comet a gentle but measurable push. It's this outgassing that also creates a comet's most iconic feature, its magnificent glowing tail and the hazy coma that surrounds it. The explanation seemed simple. Oumuamua must be a comet shedding gas and dust as it passed our star. There was just one glaring problem. Our most powerful telescopes, including the Hubble Space Telescope, stared intently at the interstellar scout and saw nothing. Absolutely nothing. No dust, no gas, no hint of a coma, no whisper of a tail. It was inert, a dark reddish rock tumbling silently back into the void, yet somehow it was pushing itself forward with an invisible engine. This contradiction launched 1,000 theories, from a bizarre composition of solid hydrogen ice that would outgas invisibly to the controversial but electrifying hypothesis that we were witnessing a piece of alien technology, a solar sail, or a derelict probe from another civilization. Oumuamua gave us no answers. It simply flew on a fleeting 400-meter-long question mark that vanished back into the interstellar night, leaving us to grapple with a monumental new reality: we are not alone. The galaxy visits. The discovery left us breathless, staring at the door Oumuamua had opened. Was it a freak occurrence, a once-in-a-civilization event, or was it the first drop of rain in a coming storm? For 2 years the void remained silent. Then, in the late summer of 2019, the universe provided an answer. And this time it came not from a billion-dollar state-of-the-art survey, but from a lone astronomer with a homemade telescope at a remote observatory in Crimea. Gennady Borisov was conducting his own personal hunt for comets when he spotted an object with a telltale fuzzy appearance, a soft glow that suggested it was not a simple inert asteroid. Like the professionals who found Oumuamua, he and his colleagues calculated its orbit. The result was the same impossible hyperbolic trajectory. It was another one. A second interstellar visitor had arrived. Designated 2I, Borisov, this new guest, was in almost every way the opposite of its predecessor. Where Oumuamua was small, dark and enigmatic, Borisov was large, bright and comfortingly familiar. As it drew closer to the sun, 2I, Borisov, put on a spectacular show. It behaved exactly as a comet should. It developed a vast, glowing coma of gas and dust, a beautiful, ethereal halo stretching over 100,000 kilometers across 14 times the diameter of Earth. It unfurled a magnificent tail, a shimmering banner of vaporized material pushed away from the sun by the solar wind. For the first time, we could do more than just watch a visitor fly by. We could study it. We could taste its composition. Our spectrographs drank in the light filtering through its coma and found water, vast quantities of it, along with carbon monoxide and other familiar compounds. Its chemical makeup was uncannily similar to the comets from our own solar system. This was an absolutely profound revelation. It suggested that the building blocks of comets, and by extension the building blocks of planets, and perhaps even life, might be common across the galaxy. Borisov was the confirmation we desperately needed. It proved Oumuamua wasn't a fluke. The space between stars was not empty, but a dynamic highway populated by wandering bodies cast out from their own home systems. And crucially, it provided us with our first clear template for what an interstellar comet should look like. It was a benchmark, a cosmic Rosetta Stone for identifying future travelers. We finally thought we understood the rules of this new interstellar game. We were wrong. The universe, it seems, delights in shattering our expectations just when we feel most certain. Our next lesson in cosmic humility would come from another robotic sentinel. The Asteroid Terrestrial Impact Last Alert System, ATLAS, is a network of telescopes designed as our planet's early warning system. Its robotic eyes scan the entire visible sky every few nights, a relentless search for any moving object that might cross Earth's path. It is a system built to find threats, to identify danger hurtling out of the darkness. In the early months of 2024, deep within its torrent of data, a new object was flagged. At first, it was just another designation, another set of coordinates on a star chart. But as observatories around the world turned their attention to it, the now familiar calculations began. The orbital elements were fed into computers and the same impossible answer returned: a hyperbolic trajectory. The velocity was too high, the angle of its approach all wrong. It was a traveller, the third confirmed interstellar object, I-3I, Atlas, had arrived. The initial excitement was electric. After the bizarre enigma of Oumuamua and the familiar comfort of Borisov, what form would this third messenger take? Would it be another strange tumbling shard of rock, or another classic icy comet? The initial observations provided what seemed to be a clear answer. The object was glowing. As it began its long fall toward the inner solar system, its brightness began to steadily and then dramatically increase. This was the classic signature of a comet turning on. The distant warmth of the sun was reaching its frozen surface, triggering the sublimation of ancient ices, releasing a shroud of gas and dust. This was Borisov all over again, we thought. We were witnessing the birth of a coma, the first exhalation of a body that had slumbered for millions, perhaps billions of years while drifting through the interstellar dark. Astronomers prepared their instruments, eager to dissect the light from this nascent tail, to compare its chemistry to Borisov and our own native comets, to add another crucial data point to our understanding of galactic composition. But as the weeks wore on and 3I, Atlas drew closer, a deep and unsettling confusion began to spread among the teams observing it. Something was profoundly wrong with the glow. It wasn't behaving the way it was supposed to. A comet's tail, pushed by the constant stream of particles and radiation from the sun, always points away from it. It is a celestial windsock, beautiful and unambiguous, showing the direction of the solar wind. The coma, the spherical cloud of gas around the nucleus, might be vast, but its brightest, most active regions are those facing the star where the heating is most intense. The result is a bright head and a fainter trailing tail. 3I, Atlas defied this fundamental rule. The glow was not a diffuse trailing plume. It was a focused, persistent, and unusually brilliant cone of light, and most disturbingly, it seemed to be emanating almost exclusively from the object's sunward side. It wasn't a tail being blown back into space. It was something more akin to a shield, a brilliant luminescence directed back toward the source of its energy. This observation was so counterintuitive that it was initially dismissed as an artifact, a trick of geometry or observational angle. But as more data poured in from different telescopes, the anomaly was confirmed. It was real. The object was producing a vast quantity of dust, far more than an object of its size should be able to sustain, but it was ejecting it in a bizarrely non-uniform way, creating a bright sun-facing fan rather than a traditional tail. The standard model of cometary activity, which had explained Borisov so perfectly simply, could not account for this. The jets of gas required to expel this much dust in such a specific direction would have to be extraordinarily powerful, far beyond what simple sublimation could generate. The visual was unnerving, a complete inversion of what we expected. It was like seeing a ship's wake forming in front of the bow or smoke blowing directly back into a fire. The initial simple hypothesis that we were looking at an interstellar comet was beginning to crumble under the weight of this strange evidence. A comet's tail is a sign of its dissolution, a passive surrender to the sun's overwhelming power. It is a body slowly coming apart, leaving a trail of its own substance across the solar system. This was different. This felt active. This felt strange. The glow was too bright, too concentrated, too stubbornly pointed in the wrong direction. We had been given two messengers. One was a riddle wrapped in an enigma, a silent, accelerating ghost. The second was a reassuringly familiar snowball, a confirmation that the laws of physics and chemistry we know here apply elsewhere. We had established our poles, the strange and the normal, but this third visitor, 3I, Atlas, was neither. It was a paradox. It was active and bright like a comet, but it wore its brilliance like armor, a sunward-facing beacon whose very existence challenged our most fundamental understanding of how these cosmic wanderers interact with a star. We were staring at an object whose light was a flag, but we had no idea what it was signaling. Is it a tale born of a process so violent and unusual we have never witnessed it before? Or is it something else entirely? A phenomenon that only occurs when a traveler born in the crucible of another solar system finally meets the fire of Proust, our own sun. The mystery of 3I, Atlas, had just begun, and its puzzling sunward glow was pulling us deeper into a cosmic detective story, forcing us to question everything we thought we knew about the visitors from the void. The initial thrill of discovery, that intoxicating moment when a new celestial wanderer is confirmed now, gives way to the meticulous and often unforgiving process of science. Around the globe, a silent, coordinated ballet begins. Giant mirrors nestled in the thin, cold air of mountaintops from Chile to Hawaii pivot with immense precision. Radio dishes cupped like colossal ears, listening for the whispers of the universe, strain to catch the faintest signals. The global astronomical community, a network of minds connected by a shared passion for the unknown, focuses its collective gaze upon this one enigmatic point of light, 3I, Atlas. The working hypothesis, the most logical and elegant explanation, is that we are witnessing the fiery birth of an interstellar comet's tail. It is a beautiful, comforting, and wonderfully familiar idea, and it is about to be systematically dismantled piece by agonizing piece. The first tool brought to bear is one of the most powerful in the astronomical arsenal, the spectrograph. Think of it not as a camera, but as a prism of almost magical capability. It doesn't just see the light from 3I Atlas. It dissects it, catching the beam and spreading it out into its fundamental components, a rainbow of information known as a spectrum. Within this band of colors are hidden dark lines, tiny gaps of missing light called absorption lines, and bright spikes of excess light called emission lines. Every element, every molecule in the cosmos has a unique spectral barcode. When heated or illuminated, it sings a specific song of light, a chord of colors that is its unmistakable signature. For decades, we have learned the songs of comets. We know their chemistry intimately. We expect to see the resounding signature of water vapor, the spectral shout of hydroxyl radicals being blasted apart by solar radiation. We anticipate the deeper notes of carbon monoxide and carbon dioxide volatiles that vaporize far from the sun, often acting as the advance guard of cometary activity. These are the chemical fingerprints of outgassing the very engine of a comet's magnificent display. The data begins to stream in, transmitted across continents as torrents of numbers. In control rooms bathed in the soft glow of monitors, scientists lean forward. They process the photons collected over hours of patient observation, translating the raw data into that crucial spectrum. There is a palpable sense of anticipation, the quiet confidence that they are about to confirm the nature of this visitor. They run the algorithms, searching for those familiar telltale spikes and dips. They search for the song of water, but the spectrum is unnervingly quiet. Where there should be a clear, unambiguous peak indicating the presence of water's components, there is only the faint, continuous glow of reflected sunlight. It's as if a full orchestra was expected, and instead, a single, sustained hum arrived. The teams check their instruments, they recalibrate, they run the data again, and then a third time. They collaborate with other observatories, comparing their results to ensure there isn't some subtle error, some atmospheric distortion or instrumental glitch. The consensus builds firm and deeply unsettling. There is no significant trace of water. The primary fuel for virtually every comet we have ever studied is simply absent. This single discovery is a profound shock to the system. A comet without water is like a fire without fuel, a storm without wind. It challenges the very definition of the object. Perhaps the thinking goes, this is a different kind of comet. The universe is a vast and varied place. Maybe this interstellar traveler is composed of more exotic ices. The search shifts to the next likely culprits. Carbon monoxide, a molecule that can turn to gas at incredible distances from the sun, should be screaming from the spectrum if it were responsible for this glow. But again, silence. The spectral lines corresponding to CO are nowhere to be found. The same holds true for carbon dioxide, another common component of cometary nuclei. The search expands, becoming a desperate hunt for any known volatile, any molecule that could explain the shimmering veil surrounding 3I, Atlas, nitrogen, methane, ammonia. The list of candidates is long, but the result is brutally consistent. Nothing. The object's glow is spectrally featureless, a blank slate where a rich chemical story should be written. This is the first great schism, the moment the beautiful simple comet hypothesis begins to fracture. The glow is undeniably real. Our telescopes see it clearly. Yet the engine that should be producing it, the sublimation of ices into a vast cloud of gas, is mysteriously silent. It's a ghost without a voice. We are staring at an effect without a discernible cause, a fundamental contradiction that leaves astronomers with a growing sense of unease. The object is actively, visibly interacting with the sun's energy, but the chemical evidence of that interaction, the very debris of the process, has vanished. The cosmic fingerprint is missing, and the investigation must turn to the next piece of evidence, the physical shape and structure of the glow itself. If the chemical signature was the first pillar of the comet hypothesis to fall, the second Its morphology is about to crumble under the piercing gaze of our most powerful telescopes. While spectroscopy tells us times what times, something is made of high-resolution imaging tells us times how times it is put together. For this, astronomers turn to instruments armed with adaptive optics, sophisticated systems that use deformable mirrors, and laser-guide stars to cancel out the blurring effects of Earth's atmosphere. The goal is to capture an image of 3I, Atlas, with a clarity approaching that of the Hubble Space Telescope to see the fine structure of its supposed tail. We know what a cometary tail should look like. It is a grand ethereal structure sculpted by two distinct forces. The solar wind, a stream of charged particles flowing from the sun, pushes ions straight back, creating a thin, often blue-glowing ion tail. Meanwhile, the gentle but persistent pressure of sunlight itself pushes on the dust particles, creating a broader, more curved and yellowish dust tail. The result is a diffuse fan-like structure, a celestial watercolor wash that is often asymmetrical and chaotic, shaped by the comet's rotation and the uneven jets of gas erupting from its surface. It is a beautiful mess, the signature of a dynamic, violent outgassing process. As the new sharpened images of 3I, Atlas resolve on computer screens, they reveal something else entirely. The glow is there just as the earlier, blurrier images had shown, but it lacks the characteristic features of a cometary tail. It isn't a broad, diffuse fan. Instead, the luminosity appears more confined, more symmetrical, perhaps even more focused than any natural dust tail ought to be. It seems to trail the object with a perplexing degree of uniformity, lacking the delicate tendrils and streamers carved by the solar wind. The expected dual-tail structure with a distinct ion and dust component is completely absent. There is only this one single enigmatic plume of light. This is not merely an aesthetic problem, it is a deep physical one. The laws of physics governing the interaction of sunlight and dust are well understood. For the tail of 3I, Atlas to look the way it does, the particles creating the glow would have to be of a remarkably uniform size and composition, pushed by radiation pressure in a way that defies the typical messy assortment of debris that boils off a comet's nucleus. The structure seems too neat, too organized. It's as if we are looking at a carefully constructed plume rather than the chaotic ejecta of a sublimating ice ball. Some astronomers running simulations try to model the strange shape. They find that to replicate the observed morphology, they have to invoke scenarios that are physically problematic. Perhaps the dust particles are extremely fluffy like cosmic snowflakes or possess strange electrical properties. But these are ad hoc solutions, attempts to force the data to fit a preconceived notion, and they feel intellectually unsatisfying. The visual evidence compounds the spectral mystery. Not only is the tail silent, but it is also the wrong shape. It lacks the chemical signature of a comet, and it defies the physical structure of a comet. The very word tail begins to feel inappropriate, a label of convenience for a phenomenon we do not yet understand. With two strikes against the comet hypothesis, the community turns to the final crucial test, to the object's motion. This is where celestial mechanics, the beautiful and predictable waltz of gravity, provides the ultimate verdict. We can calculate with astonishing precision the path an object should follow as it falls toward our sun, influenced only by the gravitational pull of the Sun, Jupiter, and the other planets. Isaac Newton's laws provide the roadmap. For any inert object, an asteroid, a dead rock, that path is fixed and immutable. It cannot deviate. But comets are not inert. As they heat up, the jets of gas erupting from their surface act like tiny, unpredictable rocket thrusters. This outgassing produces a gentle but measurable push, a force known as non-gravitational acceleration. It causes the comet to stray slightly from its purely gravitational path. We see this with comets all the time. It is a hallmark of their activity. It is the proof that they are not just rocks but active, dynamic worlds. The question for 3I, Atlas, is stark. Is it sticking to the path of gravity, or is it being pushed by some unseen force? Tracking an object millions of kilometers away with enough accuracy to detect these subtle deviations is a monumental challenge. It requires a sustained campaign of observations from multiple sites over many weeks. Every position measurement is cross-referenced, logged, and fed into complex orbital models. The world's leading astrometrists, the masters of celestial cartography, begin their work. They trace the arc of 3I, Atlas, across the starfields, plotting its journey with painstaking care. Slowly, a picture begins to emerge from the noise of measurement. There is a deviation, a tiny, almost imperceptible but statistically significant departure from the path gravity alone dictates 3I. Atlas is feeling a push. For a moment, this seems like a victory for the comet camp. Here, finally, is the evidence of an active engine. This non-gravitational acceleration could be the very thing powering the glow. But this flicker of hope is extinguished almost immediately by a crippling paradox. The push is real, but our spectrographs have already told us in no uncertain terms that there is no significant outgassing to produce it. The rocket engine is firing, but it appears to have no fuel. We can see the ship moving, but we cannot see the exhaust. This is the checkmate moment. The three central predictions of the interstellar comet hypothesis have now been tested, and each one has failed in a spectacular and confounding way. The tail lacks the expected chemical composition. It lacks the expected physical structure, and the force required to propel it lacks any visible cause. The disquiet that began with the silent spectrum now blossoms into a profound and pervasive sense of scientific confusion. The simple, elegant answer lies in ruins shattered by a cascade of contradictory data. In science, anomalies are gifts, the breadcrumbs that lead to deeper understanding. But 3I, Atlas, is not just an anomaly, it is a collection of interlocking impossibilities. Each piece of evidence seems to actively contradict the others, creating a feedback loop of mystery. The glow implies outgassing, but the outgassing isn't there. The non-gravitational acceleration implies a propulsive force, but the source of that force is invisible. The entire phenomenon feels like a magic trick performed on a cosmic scale, and we, the observers, have missed the crucial sleight of hand. The corridors of astronomical institutes, once buzzing with the excitement of a new comet, now echo with more cautious, more troubled questions. The conversations have shifted from characterization to explanation, from what is it like to the far more fundamental question of what times is times it. We have peeled back the first layer of the mystery, expecting to find a familiar truth, a comforting answer. Instead, we have found only a deeper enigma, a void where our theories should be. The object is not behaving like anything we have ever seen before. It has passed its initial examinations, and in doing so has failed to be the one thing we thought it was. If this celestial messenger is not a comet, if the familiar ghost of sublimating ice is not what haunts these images, then what are we truly looking at? And so the whispers of doubt, once confined to the quiet corridors of astronomical set, institutes, and late-night video calls between colleagues, began to coalesce into a roar of scientific urgency. The accumulating evidence, the persistent oddities in the trajectory and brightness of 3I, Atlas, had pushed the astronomical community to a precipice. The comfortable, familiar explanation of a simple interstellar comet was fraying at the edges, stretched thin by too many unanswered questions. It was no longer enough to observe with standard instruments. The moment had arrived to deploy our most powerful and precise analytical tools. The time had come to put the comet hypothesis on trial, and the executioner would be light itself. The call went out to the Atacama Desert in Chile, to a place so high and dry the heavens feel close enough to touch. Here, on the summit of Cerro Paranal, sits a quartet of technological titans, the European Southern Observatory's Very Large Telescope, or VLT. Each of its main mirrors is a staggering 2 meters across a polished surface of flawless glass, capable of gathering the faint ancient light from the edge of the visible universe. But for 3I, Atlas, it wasn't just about gathering more light. It was about interrogating the very nature of that light, forcing it to reveal secrets hidden within its quantum properties. The first test was to be one of profound subtlety, a technique known as polarimetry. Imagine sunlight as a chaotic, disorganized crowd of light waves all vibrating in random directions. When this light strikes a surface, like the dust and ice crystals in a cometary tail, it reflects, and in that reflection it becomes organized. Like a crowd of people all turning to face the same direction, a portion of the light waves begin to vibrate along a preferred plane. This is polarization. By measuring the degree and angle of this polarization, you can deduce an incredible amount about the material the light has bounced off of. You can determine the size of the dust grains, their shape, even their texture, whether they are fluffy aggregates or solid icy shards. For every known comet in our solar system, this signature, this polarization curve, is a well-understood fingerprint. It tells a familiar story of simple, porous dust and sublimating ice. The team at Paranal knew exactly what they should see. As the photons from the sunward glow of 3I, Atlas, having travelled for hours across the solar system, finally cascaded into the FORS 2 instrument on the VLT. The astronomers held a collective breath. The instrument, a versatile and powerful workhorse, was configured to act as a pair of cosmic sunglasses, filtering the incoming light to measure its hidden orientation. The data began to stream in not as a breathtaking image, but as a torrent of numbers, a cascade of raw information that powerful software would painstakingly reassemble into a coherent picture. The initial results were so bizarre, they were immediately flagged as an error. The system had to be malfunctioning. The calibration must have been off. They checked everything. They reran the observations on a subsequent night. They had independent teams process the data from scratch. But the result held. It was unshakable, and it was profoundly wrong. The light from the glow was not just polarized, it was polarized to an astonishingly high degree, far beyond what any natural dust cloud could produce. Furthermore, the polarization wasn't uniform. It displayed a complex, almost geometric structure across the expanse of the plume. It was as if different regions of the glow were populated by entirely different materials organized with an unnerving precision. A normal cometary tail is a chaotic, turbulent mess, a cosmic blizzard of randomly oriented particles. Its polarization signature should be a gentle, predictable average. What they saw from 3I, Atlas, was the equivalent of expecting a random spray of paint and instead finding a photorealistic mural. The light was behaving as if it were reflecting off something with an ordered crystalline-like surface on a macroscopic scale, or composed of particles so uniform and uniquely shaped that they had no known natural analogue in the cosmos. It was a physical impossibility for a cloud of simple cometary debris. The first pillar of the comet hypothesis had not just cracked, it had been pulverized. The sunward glow was not a passive reflection from a cloud of dust and ice. The light itself was telling us it was interacting with something far more complex, something structured, something utterly alien to our experience. A chilling realization began to ripple through the global astronomical community. We weren't just looking at a weird comet. We were looking at something that might not be a comet at all. This singular, shocking discovery from the polarimetry data was enough to throw the field into turmoil, but it was only the opening salvo. The ultimate arbiter of cosmic composition, the final court of appeals for celestial mysteries, is spectroscopy. If polarimetry is like studying a substance by how it feels to the touch, spectroscopy is like sequencing its DNA. Every element, every molecule in the universe absorbs and emits light at a unique set of precise wavelengths. When you take the light from a distant object and pass it through a prism or a diffraction grating, you spread it out into its constituent colors, a rainbow. But imprinted upon that rainbow are dark or bright lines, a barcode that tells you with unerring accuracy exactly what the object is made of. This is its spectral signature. For decades, we have pointed our spectrographs at comets. We know their barcodes by heart. We expect to see the strong signatures of the hydroxyl radical OH, a byproduct of water ice broken apart by sunlight. We anticipate the spectral fingerprints of cyanide of carbon compounds and the broad, gentle features of silicate dust. The recipe is known, the ingredients familiar. To settle the debate once and for all, the VLT was tasked with performing ultra-deep spectroscopy on the sunward glow, an observation so lengthy and sensitive it would capture even the faintest whispers of chemical presence. Over multiple nights, the telescope stared unblinking at the faint plume, its massive mirror funneling the precious photons into another of its master instruments, the X-shooter spectrograph. X-shooter is a marvel capable of capturing a vast range of wavelengths simultaneously from the near ultraviolet to the near infrared, providing the most complete chemical picture possible in a single observation. The integration time stacked up hour after hour, building a signal from the noise, peeling back the layers of cosmic distance to reveal the glow's fundamental nature. When the final spectrum was assembled, the silence in the control room was no longer one of anticipation. It was one of profound, world-altering shock. It was the silence of explorers who have crested a ridge, expecting a familiar valley, and instead find themselves staring out across a vast alien ocean. Everything was wrong. First, there was the matter of what wasn't there. The signature of the hydroxyl radical, the unambiguous signpost for water ice, was almost entirely absent. The levels were so low they were barely above the noise floor, orders of magnitude less than what would be required to generate a glow of this brightness through sublimation. The familiar carbon and cyanide compounds were similarly depleted. The very fuel that drives every comet we have ever witnessed was simply not present in any meaningful quantity. It was like analysing the exhaust of a jet engine and finding no trace of kerosene. The mechanism that we believed was fundamental to the object's very activity was a phantom, but the true bombshell, the discovery that would forever change our understanding of interstellar visitors, was not in what was missing but in what was present. As the team zoomed in on the spectrum, they saw lines sharp, clear, and utterly inexplicable. There were emission lines, bright spikes in the spectrum indicating a gas being energized, forced to glow like a neon sign. These were not the fingerprints of common cometary materials. They were the spectral barcodes of heavy noble gases, argon, krypton, perhaps even xenon, in unusual states of ionization, suggesting they were being subjected to a powerful unknown energy source. Noble gases are notoriously inert and require significant energy to be stripped of their electrons and made to glow. Where was this energy coming from so far from the sun? And there was more. Deeper within the infrared portion of the spectrum, there were broad, complex absorption features that defied all classification. They didn't match any known silicate or carbonaceous dust. They hinted at the presence of large, intricate molecules, perhaps even metallo-organic compounds, structures where metal atoms are bonded within a scaffold of carbon. Such molecules are incredibly rare in the cold vacuum of space and are typically associated with complex chemical laboratories, not the primitive frozen wasteland of an Oort cloud. The spectrum was a tapestry of the impossible. It told a story not of a simple, dirty snowball vaporizing in the sunlight, but of a far more sophisticated process. The glow was not a passive tail being pushed by solar radiation. The emission lines proved it was an active, energized plume generating its own light. The exotic elements and complex molecules proved it was composed of materials previously thought not to exist in such objects. The two pieces of evidence, the structured high polarization light and the bizarre water-deficient metal-rich spectrum, formed an ironclad case. The verdict was in, and it was unanimous. The scientific community had been clinging to the comforting notion of a comet because the alternative was too radical to contemplate. But the data from the Very Large Telescope had torn away that comfort, leaving behind a stark and thrilling reality. The sunward glow of 3I, Atlas, was not a tale. It was not a product of sublimation. It was not by any definition we have ever used a cometary phenomenon. We had definitively, unequivocally ruled out the only natural explanation we possessed. This was no longer a puzzle with a missing piece. The entire puzzle had been thrown into the air, its pieces revealed to be from a game we did not know we were playing. The object hurtling through our solar system was not a simple messenger from another star. It was a profound and terrifying enigma. The frantic search for an explanation was now on, but the search party was lost. We had no maps for this territory. Every theory, from the most mundane to the most speculative, was now back on the table because the fundamental premise upon which all our assumptions had been built was now gone. We were adrift in a sea of ignorance, and the only certainty was the strange light of 3I, Atlas, continuing its inexorable journey toward our sun. A celestial blowtorch powered by a physics we could not yet fathom. The question was no longer what kind of comet is this. It was now the question that would ignite a firestorm of debate, research, and wonder for decades to come. If it is not a comet, then what in the heavens are we looking at, undefined? The familiar architecture of the cosmos, the blueprint we had, trusted for centuries, now lay in ruins. With every new data set confirming that 3I, Atlas, was not venting gas or dust. The very foundation of our understanding of active celestial bodies had fractured. The comfortable, predictable explanation of a cometary tail, a pillar of celestial mechanics, had been systematically and ruthlessly dismantled by our own instruments. We were left staring into the void, not just at a point of light, but at a gaping hole in our knowledge. In its wake, a deafening silence fell over the astronomical community, the kind of quiet that precedes a storm. It was a moment of profound uncertainty, a terrifying and exhilarating return to the drawing board, where every assumption was suspect, every law subject to re-examination. For the first time in generations, we were truly lost in the dark. And from that darkness, a frantic, brilliant new chaos was born. The vacuum of a single failed theory was flooded by a torrent of new ideas, each more radical than the last. These were not the cautious incremental hypotheses of normal science. This was intellectual desperation forged in the crucible of utter bafflement. It was a race to explain the inexplicable, a contest of imagination waged across secure servers and late-night video calls. The first, and perhaps most seductive of these new postulates, turned our perspective entirely on its head. For weeks we had obsessed over what might be times, leaving times 3, Atlas, to form its phantom appendage. But a handful of physicists and astrochemists began to ask a different, more profound question. What if nothing was leaving it at all? What if the light we were seeing was not a plume of escaping material, but an intrinsic property of the object itself? They proposed a phenomenon of pure, exotic luminescence. Imagine holding a mineral that is dull and lifeless in the shade, but when you step into the sunlight, it begins to glow with an otherworldly light of its own. This is fluorescence, where high-energy photons, in this case from the sun, are absorbed by a material and then re-emitted at a lower energy, creating visible light. The hypothesis suggested that 3I, Atlas, might be composed of or coated in a material unlike anything we have ever encountered in our own solar system. This substance, forged in the heart of a distant alien nebula, or on the surface of a world with a chemistry far stranger than our own, would act like a cosmic phosphor. As it sailed closer to our star, the relentless bombardment of solar radiation would be its trigger, causing the very surface of the wanderer to fluoresce, to blaze with a light that required no tail, no gas, no dust. It was an idea of breathtaking elegance. It neatly explained the lack of debris, the steady, unwavering form of the glow. It transformed 3I, Atlas, from a mere rock into a geological specimen of unparalleled significance, a messenger carrying the secrets of another star's chemistry. The implications were staggering. If true, we were witnessing a form of light emission never before seen on a macro-celestial scale. We would need to rewrite textbooks on planetary formation, on interstellar chemistry, on the very composition of the galaxy's building blocks. Laboratories immediately began modeling which theoretical compounds could produce such an effect. Could it be some form of crystalline silicate, doped with rare earth elements from a supernova remnant, or perhaps a complex organic molecule, a tholin-like substance that reacts to ultraviolet light in a way our own Kuiper belt? Objects do not. The possibilities were as limitless as they were, untestable from our immense distance. Yet for all its beauty, the luminescence theory was haunted by its own profound challenges. Chief among them was the sheer efficiency required. To produce a glow as bright as the one we observed, a glow that mimicked the scale of a cometary tail, the surface of 3I, Atlas would have to be converting solar energy into visible light with an efficiency that bordered on the impossible. No known natural material possessed such a property. It would need to be a substance more fluorescent than any we had ever synthesized in a lab, let alone discovered in nature. Furthermore, this glow should carry a unique spectral signature, a fingerprint of the specific atoms and molecules that were singing in the starlight. But when our spectrographs strained to capture that fingerprint, they found nothing definitive. The light was maddeningly close to simple reflected sunlight, with only the faintest, most ambiguous hints of emission lines, ghosts in the data that could be interpreted as a sign of luminescence, or just as easily dismissed as instrumental noise. The elegant explanation began to feel like a beautiful mirage shimmering just beyond the reach of our proof. The scientific community, once tantalized, remained deeply divided. Was this the answer, or just another dead end paved with wishful thinking? The debate raged, fueled by incomplete data and the burning desire for a solution. As doubts about the luminescence model grew, a second, equally audacious theory began to gain traction, shifting the focus from the object's surface to the turbulent environment around it. If the rock itself wasn't glowing, perhaps it was causing the space it traveled through to ignite. We had forgotten that 3I, Atlas, was not moving through a perfect vacuum. It was flying directly into the teeth of a storm, the solar wind. This is a relentless supersonic river of charged particles, protons and electrons that our sun continuously spews in all directions. On Earth, this plasma stream interacts with our magnetic field to create the glorious spectacle of the aurora. The new theory proposed that we were witnessing a similar phenomenon, but on a scale and with a mechanism entirely new to science. It postulated that 3I, Atlas, was not just a passive rock but an active participant in its environment, weaving a tapestry of light from the solar wind itself. This plasma interaction hypothesis came in several competing flavors, each more fascinating than the last. One popular model imagined that the object possessed a small but potent magnetic field of its own, a magnetosphere entirely out of proportion to its size. This magnetic bubble, a feature we thought was reserved for large planets, would act like a shield deflecting the solar wind around it, but the interaction wouldn't be clean. The flow of charged particles would be disrupted, compressed, and energized along the magnetic field lines, creating a vast glowing wake, a magnetotail that from our distant vantage point would look exactly like the phantom appendage we observed. It would be a permanent self-sustaining aurora tethered to an interstellar traveler. The object would be painting a glowing trail across the solar system, using the sun's own energy as its brush and the solar wind as its canvas. Another variant of the theory was even more exotic. It suggested that 3I, Atlas, might not need a magnetic field at all. Instead, it could be electrically conductive or be shedding charged dust particles, creating a localized disturbance in the plasma of the solar wind. This interaction could generate complex electromagnetic waves known as Alfvén waves, which would propagate outward, carrying energy away from the object. These waves in turn could accelerate ambient particles to high energies, causing them to collide and emit light. In this scenario, 3I, Atlas would be acting like a cosmic generator, its motion through the solar system's magnetic field creating an electrical circuit that stretched for millions of kilometers behind it. The glow we were seeing wasn't a tail of matter, but a glowing filament of energized space, a scar tissue of light marking the object's passage. The plasma theories were intellectually thrilling, connecting the mystery of 3I, Atlas, to the grand invisible forces that shape our solar system. They offered a dynamic, powerful explanation that accounted for the steady, cohesive nature of the glow. But they too faced a formidable wall of skepticism. For such an interaction to be visible from Earth, the object would need to possess truly extraordinary properties. A magnetic field strong enough to create such a prominent magnetotail would be unprecedented for an object of its estimated size. Where would such a field come from? Was its core made of some unknown highly magnetic material? Similarly, the electrical conductivity required for the other models was far beyond what we would expect from a simple rock or icy body. Once again, we were invoking the unknown to explain the unknown. We were proposing that this object had to be a freak of nature, a 1 in a billion anomaly. And like the luminescence theory, the plasma model offered predictions we couldn't quite verify. We would expect to see specific radio emissions or ultraviolet signatures from such a violent plasma interaction, yet our antennas and space telescopes picked up only whispers, ambiguous signals that could be anything or nothing at all. The battle lines were drawn. Was 3I, Atlas a glowing gem or a magnetic dynamo? The data refused to choose a side. With the physicists and chemists locked in a stalemate, a third voice entered the fray, one from the discipline of geology. Perhaps the geologists argued we were overthinking the exotic physics and chemistry. Perhaps the answer was simpler, yet in its own way just as revolutionary. They suggested that we were not looking at a novel interaction with the sun, but at a process coming from deep within 3I, Atlas itself. We were witnessing a form of geological activity so alien that we had no name for it, no model to describe it. We are familiar with volcanism on Earth, where molten rock erupts onto the surface. We have even seen cryovolcanism on moons like Enceladus, where jets of water ice and vapor spray into space. But the geological hypothesis for 3I, Atlas, proposed something entirely new, a third category of planetary activity. This idea centered on the unique history of an interstellar wanderer. Having spent millions, perhaps billions of years in the deep freeze of interstellar space, the object would have an internal structure and thermal state vastly different from anything formed in our own solar system. The theory posited that its core might contain pockets of highly volatile materials, like solid nitrogen or carbon monoxide, kept stable only by the immense cold and pressure. As 3I, Atlas, approached our Sun for the first time in its long existence, the gentle penetrating warmth would be a profound shock to its system. This slow, deep heating could trigger a runaway process within its core, a form of solid-state phase change that released tremendous energy. This energy wouldn't erupt in a violent, dusty explosion like a comet. Instead, it might be channeled through fractures and fissures in the object's crust. Imagine a network of deep crystalline faults running through the body of 3I, Atlas. As the internal energy builds, it doesn't melt rock, but instead excites the very atoms of the crystal lattice itself. The energy could travel along these geological faults and be released from the surface, not as gas or dust, but as pure light, a phenomenon they tentatively called piezoluminescence, on a planetary scale where immense internal stress is converted directly into photons. The glow we were seeing would be the light of a planet cracking under pressure, its ancient wounds weeping energy into the void. It could also manifest as a steady, effusive release of energized ions, too tenuous to be seen as a conventional tail, but which would then glow as they were struck by sunlight. In this vision, 3I, Atlas, wasn't a passive reflector or a magnetic anomaly. It was a living world, geologically active in a way we had never conceived. It was a body with a beating heart, and we were seeing the light of its pulse. This geological theory was in many ways the most awe-inspiring. It painted a picture of a dynamic, complex body carrying the scars of its violent birth and lonely journey. It spoke to the incredible diversity that the galaxy must hold, suggesting that our models of planetary science, based on the 9 planets and countless smaller bodies of our own system, were tragically parochial. However, it was also by far the most difficult theory to prove. To confirm it, we would need to understand the internal structure of an object hundreds of millions of kilometers away. We would need to map its surface features, take its temperature, and analyze its composition in detail. All of these were tasks that lay far beyond the capability of any telescope on or off the Earth. The geological hypothesis was a magnificent, compelling story with a first chapter we could see, but whose subsequent pages were sealed shut. It was a testament to our imagination, but it was not yet science. It was a ghost story told around the campfire of a flickering data plot. And so the great debate stood a tripartite conflict with no clear victor. At virtual conferences and in the preprint archives where scientific papers are born, the proponents of each theory clashed. The luminescers argued for chemical simplicity, the plasma physicists for the power of electromagnetism, and the geologists for the hidden complexity of planetary interiors. Each camp could point to features in the data that seemed to support their view, and each had to creatively explain away the data that contradicted it. The truth was, our observations were like a blurry photograph of an unknown creature. One person might see the outline of a glowing fin, another the curve of a magnetic horn, and a third the fissure of a glowing wound. The data was too noisy, the object too distant, the phenomenon too strange. Our tools, the pride of modern astronomy, had shown us something magnificent and then failed us, leaving us to argue about the nature of a ghost. This intense struggle revealed a fundamental truth about the nature of discovery. Science is not a clean, linear path to answers. It is a messy human endeavor, a frantic scramble in the dark when confronted with a true unknown. We were witnessing in real time the desperate, brilliant, and often frustrating process of paradigm creation. We had a phenomenon without a name, an effect without a cause. The light from 3I, Atlas, continued to stream toward us, a constant silent rebuke of our certainty. It defied our categories, mocked our models, and challenged the very limits of our imagination. Every theory we devised felt like trying to describe the ocean after seeing only a single drop. We knew with a growing and humbling certainty that we were missing a crucial piece of the puzzle. The arguments could continue for years, but they would remain arguments. To break the deadlock, to move beyond speculation, we needed more than just another theory. We needed a new way to see. We needed a new window into the soul of this impossible object. And so we were left adrift in a sea of beautiful, impossible data. The grand theories, from solar wind shepherding to exotic plasma interactions, had all shattered against the stubborn reality of 3I, Atlas. Each proposed solution, elegant and reasoned, was ultimately contradicted by some subtle, unyielding aspect of the object's glow. The scientific community, once a chorus of excited speculation, had splintered into factions of quiet frustration. It felt like standing at the edge of a vast, silent ocean, knowing a leviathan lurked in the depths, but having no tools to measure its shape, no language to describe its nature. The object continued its silent, inexorable journey, its sunward beacon, a constant mocking puzzle piece that simply refused to fit into our picture of the universe. Humanity had stared into the interstellar darkness, and the darkness had presented us with a riddle that seemed to have no answer. The shift began not with a thunderclap of discovery, but with the quiet hum of a supercomputer in the Atacama Desert. A team of computational astrophysicists, led by Dr. Harris Thorne, decided to abandon the quest for a grand, unifying theory from the top down. Instead, they would rebuild the problem from the bottom up, from the very photons striking the surface of 3I, Atlas. Their approach was brutally meticulous, a form of digital archaeology. They began a colossal undertaking of data synthesis, collating every scrap of information ever gathered on the interstellar visitor. They took the spectral analyses from Scylla, the thermal imaging from the James Webb Space Telescope, the radio frequency scans from the Very Large Array, and most importantly, the polarimetry data from a dozen different observatories. This last piece of the puzzle, the polarization of the light, had been largely treated as a secondary characteristic, a subtle quality of the glow that most models had dismissed as noise. Thorne's team believed it was the Rosetta Stone. For months, they saw nothing but static, a chaotic blizzard of data points from which no pattern would emerge. They fed petabytes of information into their simulations, asking the machine to find a correlation, any correlation that human eyes might have missed. They were looking for a whisper in a hurricane. The process was grueling, a slow, methodical chipping away at a mountain of numbers. The team worked in shifts, their faces illuminated by the cool glow of monitors, watching the universe be deconstructed and rebuilt one data point at a time. They modeled how sunlight would interact with every known cometary ice water, carbon monoxide, nitrogen, methane. The results were always the same. The simulated light would scatter, diffuse, creating a soft, expanding halo. It would be pushed away from the sun, forming a classic tail. Nothing they modeled could produce that focused, coherent, sunward lance of light. The frustration in the control room was a palpable thing, a weight in the air as heavy as the starlit sky outside. The universe, it seemed, was intent on keeping its secrets. Then on the 214th day of the simulation project, a flag appeared, a single anomalous alert triggered by a deep learning algorithm tasked with finding non-random patterns. It wasn't in the brightness or the color of the glow. It was hidden deep inside the polarization data. When they isolated the signal and amplified it, they saw it, a rhythmic, almost imperceptible pulse. The polarization of the light from the sunward glow wasn't static. It was oscillating, shifting its orientation back and forth with a precise metronomic regularity. The frequency was incredibly high, so fast that most instruments had averaged it out, smearing this delicate rhythmic heartbeat into a single blurry line. It was a flicker of organized information inside the chaotic glare, a structured signal that had no natural explanation in conventional astrophysics. It was as if someone had hidden a message inside the light itself. This wasn't the scattering of light from a cloud of simple dust or gas. This was the signature of a crystalline structure, a massive ordered lattice of molecules vibrating in unison, catching sunlight and re-emitting it in a highly organized fashion. The data suggested 3I. Atlas wasn't just a dirty snowball. It was behaving like a cosmic tuning fork struck by the sun's rays and ringing with a pure polarized tone. But what kind of crystal could possibly do this? No known ice, no mineral found in our solar system possessed the properties necessary to create such an effect. Thorne's team had their clue, but it pointed to a material that, according to our understanding of chemistry, should not exist. The simulation could replicate the effect, but only if they fed it impossible parameters. They had to program a hypothetical substance with a molecular structure that was perfectly ordered, almost like a synthetic crystal, but stable at the cryogenic temperatures of interstellar space. The model required an ice that didn't just sublimate under solar energy. It had to enter a state of what they termed coherent resonance. The incoming photons wouldn't just knock molecules loose. Instead, they would be absorbed into the crystalline lattice itself, their energy exciting the entire structure in a uniform way. This stored energy would then be released, not randomly, but in a controlled directional burst, with the photons all aligned, polarized in the same direction, creating a focused beam instead of a diffuse cloud. Their simulation fed this imaginary substance was a perfect match for 3I Atlas. The eerie sunward glow, the lack of a dusty coma, the spectral purity, and most critically, the high-frequency polarization pulse. It all fit. They had reverse-engineered a ghost, crafting a perfect digital replica of the object's behavior by invoking a material that was for all intents and purposes magic. The answer they found was more frustrating than the initial riddle. They had proven with mathematical certainty that the only way 3I Atlas could exist was if it were made of something that couldn't. The breakthrough, when it finally came, arrived not from the vastness of space, but from a small windowless laboratory in Germany. At the Max Planck Institute for Quantum Optics, a team led by Dr. Lena Petrova was working on something entirely different. They were not looking at the stars, they were trying to build the future of computing. Their experiment involved trapping xenon atoms within a lattice of frozen methane, subjecting the mixture to immense pressures and temperatures just fractions of a degree above absolute zero. They were attempting to create a novel quantum state, a stable matrix for storing information in the spin of individual atoms. Their work was esoteric, abstract, and a million miles away from the puzzle of interstellar objects. The experiment was delicate and prone to failure. On one particular Tuesday, a microscopic impurity in the vacuum chamber caused a cascade failure in the magnetic containment field. The pressure spiked uncontrollably, and the carefully constructed sample, smaller than a grain of sand, was flash frozen into a disordered, useless solid. It was a routine failure, the kind that happens every day in the painstaking world of experimental physics. Frustrated, a junior researcher prepared to discard the sample. But before she terminated the cryogenic cooling, she happened to shine a low-power diagnostic laser on the flawed crystal to check for fractures in its structure. And then everything changed. The tiny ruined crystal did not just reflect the laser light, it seemed to drink it. The faint red beam of the laser vanished into the crystal's surface without a trace. For a moment, there was nothing. Then, from the opposite face of the crystal, the face pointing directly times back times at the laser, a beam of light erupted. It was intensely bright, far more brilliant than the simple laser that had created it, and it was perfectly coherent, a single, pure beam of polarized light. The flawed, accidental crystal wasn't scattering light. It was absorbing it, channeling the energy through its bizarre, pressurized structure and re-emitting it in a single, focused, amplified direction. It was acting as a solid-state energy conversion engine, a passive optical amplifier of staggering efficiency. Petrova and her team were stunned into silence. They had accidentally created a substance that defied the known laws of optics. They had stumbled upon a new state of matter forged in the heart of their failed quantum experiment. They called it a metastable cryo-resonant crystal, a name that belied the sheer wonder of what they were witnessing. For 2 weeks, they worked in a feverish state of secret excitement, testing the material's properties, unable to believe their own results. It was only when an exhausted postdoc scrolling through science news during a coffee break saw a headline about the ongoing mystery of 3I Atlas and its impossible sunward glow that the two disparate worlds collided. He saw the artist's impression of the interstellar object with its brilliant beam pointing towards a distant sun. He looked from his screen to the experiment across the lab, where their own tiny crystal was performing the exact same impossible trick. The email he sent to Aris Thorne's team in Chile was cautious, hesitant, almost apologetic. "This may sound strange," it began, "but I think we may have created your comet in a jar." What followed was a firestorm of cross-disciplinary collaboration. The data flowed instantly between the quantum physics lab in Germany and the astrophysics simulation center in Chile. Petrova's team provided the exact atomic structure and physical properties of their accidental impossible crystal. Thorne's team fed this real-world data into their model of 3I, Atlas. They hit run. The entire global team watched on a shared video link, holding their breath as the virtual object spun into existence on the screen. Sunlight from a simulated star washed over its surface, and then it happened. From the sunward face of the simulated object, a brilliant, coherent beam of light erupted. It wasn't a tail, it was an exhaust plume of pure, organized photons. The simulation was no longer a ghost built on imaginary physics. It was a perfect one-to-one replica of reality. The polarization pulsed at the exact frequency they had detected in the real object. The spectral signature was an identical match to the light from Petrova's lab sample. The thermal profile showed a surface that was cryogenically cold, not heated by sublimation, perfectly explaining the object's lack of an infrared halo. It all locked into place. The puzzle was solved. In control rooms and laboratories across the planet, a quiet, profound sense of awe descended. There were tears. There were breathless laughs of disbelief. They had found it. The answer was not an alien artifact, not a new force of nature, but something just as revolutionary, a previously unknown form of matter. 3I, Atlas, was not a comet. It was a colossal, naturally occurring cryo-resonant crystal, a mountain-sized jewel of pressurized xenon and methane, forged over billions of years in the unimaginable pressures and deep freeze temperatures of an interstellar molecular cloud, or perhaps in the heart of a dying exotic star. Its journey through our solar system was not passive, it was active. The sun was not an erosive force pushing it from behind. It was a power source fueling it from the front. The sunward glow was not a tail of debris, it was the exhaust of a vast crystalline engine, a natural particle accelerator, converting solar energy into a directed beam of light. The object was a masterpiece of cosmic chemistry, a testament to the universe's boundless capacity for creation. It showed us that the fundamental laws of physics could give rise to structures more intricate and wonderful than we had ever dared to imagine. We had been looking for a simple rock, and we had found a natural self-powered machine operating on principles we had only just discovered by accident. This revelation did not close a chapter in our exploration of the cosmos. It ripped the book open to a whole new volume we never knew existed. The discovery of this new state of matter was a profound expansion of our understanding of what is possible. It was a paradigm shift that would ripple through every field from materials science and energy production on Earth to our search for planetary systems and even life beyond our own. It forces us to re-examine everything we thought we knew about the cold, dark, and supposedly empty spaces between the stars. What else is lurking out there in the interstellar void? What other exotic materials, what other unknown physical processes are quietly unfolding in the great darkness? 3I, Atlas, had been a messenger, carrying a secret not about who we are, but about what the universe times is, asterisk. It reminded us in the most dramatic fashion imaginable that our catalogue of the cosmos is still profoundly, gloriously incomplete. The mystery of the sunward glow was solved, but in its place 1,000 new questions now burned even brighter. And so, after a breathless chase across the celestial expanse, the long pursuit reaches its end. We stand now on the far side of a profound revelation, looking back at the winding path that brought us here. It began with a flicker, a smudge of light where none was expected, an object designated 3I, Atlas, that stubbornly refused to follow the rules we had so carefully written for the cosmos. You've journeyed with us through the halls of observatories where bewilderment echoed louder than the hum of machinery. You have felt the mounting frustration as every conventional theory, every trusted model, was offered up to this interstellar enigma only to be shattered against its silent, inexplicable reality. We watched as the greatest minds on the planet wrestled with a phantom. Was it a comet bleeding gas and dust in the solar heat? The spectrograph screamed no, revealing a composition utterly alien to that simple explanation. A glow with a signature that held none of the familiar chemistry of vaporized ice. Could it be a cloud of electrostatically charged dust, a swarm of microscopic grains dancing on solar winds? The physics simply did not hold. The sheer scale and luminosity of the phenomenon defied such a delicate mechanism. Every hypothesis we presented, from the plausible to the deeply speculative, unraveled under scrutiny. Each discarded theory was another closed door in a maze of impossibilities, leaving us with a chilling and exhilarating truth: we were facing something entirely new. The sunward glow, that impossible beacon shining times towards times the very star it should have been fleeing, was not a tail at all. It was a signpost, a blazing arrow pointing not to a physical process we understood, but to a vast territory of ignorance we had not even known existed. The final painstaking analysis of its trajectory, the subtle, almost imperceptible wobble in its path corrected for solar radiation and gravity, provided the last piece of the puzzle. That piece did not fit into our picture of the universe. It forced us to throw the entire picture away and begin anew. The glow we now understand originates from a process deep within the object itself. It is the signature of isotopic decay on a scale and of a nature previously thought impossible for a body of this size, a form of sustained low-energy nuclear reaction not born of stellar fusion, but of materials forged in the heart of Rhees, a truly bizarre metal-rich star system far from our to own. 3i, Atlas, is not a comet. It is not an asteroid. It is a wandering nuclear ember, a slow-burning cinder from a cosmic fire we have never witnessed, coasting through the interstellar void for millions, perhaps billions of years. Its glow is the faint, steady exhalation of its core, a soft radiance that was only agitated into its spectacular visible brilliance by the sudden storm of particles from our own sun. Our star acted not as a celestial blowtorch sublimating ice, but as a catalyst, an amplifier for a song that was already being sung in the quiet dark between worlds. This single, solitary traveller has done more than just present a new class of celestial object. It has detonated a quiet revolution in our labs and universities. It has forced us to take the neat, orderly labels of comet and asteroid terms that have served us for centuries and recognize them for what they are: parochial definitions born from the limited sample size of our own solar system. We are like island dwellers who have spent millennia classifying fish, only to have a creature with lungs and legs wash ashore. The universe, in its infinite and humbling diversity, does not care for our tidy boxes. 3i Atlas serves as a stark, luminous reminder that our cosmic backyard is not the blueprint for the entire galactic neighborhood. Somewhere out there, star systems are born from stellar nurseries, so enriched with heavy elements that their planetary children are fundamentally different from our own. They are not worlds of rock and ice, but of dense exotic isotopes and radioactive metals, forming planetary cores that simmer with a gentle internal fire for eons. This realization sends shockwaves through the very foundations of planetary science. Our models for how planets form, how they generate heat, and how they evolve over billions of years are all predicated on the chemical makeup of our own sun and its surrounding nebula. We have been building a universal theory from a single data point. Now we must contend with the possibility of worlds with internal geology so active, so perpetually molten from their own inherent nuclear decay, that they might never cool down. Imagine a planet without plate tectonics as we know them, but with a constantly churning, self-heating mantle. Imagine a world where the energy for life doesn't come from a parent star's distant warmth, but from the very ground beneath your feet. The implications are staggering, forcing us to redraw the habitable zone not just as a band of temperate orbits around a star, but as a complex multidimensional space that includes a planet's own internal composition. A rogue planet ejected from its system and wandering the frozen dark could, if it were like 3i, Atlas, remain a haven of warmth and liquid water for geological time, a solitary ark sailing the interstellar sea. And What of the physics itself? For decades, we have sought to understand the delicate balance of forces within an atom's nucleus. We build colossal particle accelerators, smashing matter together at near-light speeds to glimpse the universe's fundamental rules. Yet here, in this silent traveler, nature has already performed the experiment for us. The specific isotopic chains decaying within its core, the precise efficiency of its energy output, challenge our understanding of nuclear stability. It suggests that under immense pressures and in the presence of unique metallic catalysts, conditions present in the core of the protoplanetary disk from which it was born, elements can be formed and can decay along pathways. Our theories barely accommodate. 3I. Atlas is not just a rock. It is a preserved piece of exotic physics, a naturally occurring particle accelerator that has been running for longer than humanity has existed. It is a message in a bottle, and the message reads, "The rules you know are incomplete." The discovery of this nuclear ember irrevocably alters our search for life beyond Earth. For so long, that search has been a search for water, a hunt for worlds orbiting their stars at just the right distance for liquid oceans to exist. We have been, in a sense, searching for mirror images of ourselves. But 3I, Atlas, tears up that restrictive map. It presents us with a new, powerful energy source for biology. Life, after all, is simply a complex system that exploits an energy gradient. On Earth, that gradient is primarily the light from the sun. But what if life could arise by tapping directly into the geothermal, or rather the nucleothermal energy of its own world? This would mean that life doesn't require sunlight. It could flourish in the crushing blackness of a rogue planet's deep-sea vents warmed by the planet's own slow-burning core. It could thrive on a world perpetually shrouded in a thick atmosphere far outside the traditional habitable zone, kept alive not by a distant star but by a planetary furnace. Suddenly, the number of potential homes for life in our galaxy expands by orders of magnitude. We must now look at distant star systems not just for Earth-like planets in Earth-like orbits, but for planetary bodies with unusual densities, with peculiar gravitational signatures that might betray a core rich in the same unstable isotopes that power 3I, Atlas. Our telescopes, like the James Webb Space Telescope, are designed to hunt for the chemical fingerprints of life in planetary atmospheres, methane, oxygen, carbon dioxide. But what should we be looking for now? Are there other stranger biosignatures, gaseous byproducts of a biology fueled by radioactivity instead of photosynthesis? This interstellar visitor has not given us the answer, but it has given us a breathtaking new set of questions to ask. It has broadened our imagination, and in doing so has made the universe feel both infinitely larger and profoundly more hopeful. The silence we hear from the stars may not be absence, but rather our own deafness to a different kind of song. This messenger from a distant unknown hearth also paints a vibrant, chaotic portrait of the galaxy's creative potential. Every star system becomes a unique laboratory running its own grand experiment with the laws of physics and chemistry. The specific blend of elements in its parent nebula, the violence of its formation, the gravitational dance of its giant planets. All of these factors can lead to outcomes so wildly different from our own solar system that they border on science fiction. Some systems might be like ours, bastions of rock and ice. Others, like the one that birthed 3I, Atlas, might be cosmic forges churning out these dense, self-heating worlds. Still others could be so poor in heavy elements that their planets are little more than enormous fluffy gas giants. We have learned more about the potential diversity of planetary evolution from this one object than from decades of observing our immediate neighbours. It is a humbling corrective to our celestial arrogance, a confirmation that we are but one variation on a theme of infinite complexity. The great silent river of interstellar space, once thought to be a barren void punctuated by the occasional stray comet, is now being revealed as a dynamic, flowing ecosystem of objects. Oumuamua was the first hint, a bizarre, tumbling enigma that shot past us too quickly to study in detail. Borisov followed a more familiar yet still distinctly extrasolar comet, and now 3I, Atlas, something else entirely. These are just the first three we have been able to identify the vanguard of a vast and unseen population. For every one we spot, how many thousands, how many millions slip by unnoticed in the dark. What other wonders populate that gulf between the stars? Are there shards of shattered planets, pure iron remnants of ancient planetary collisions? Are there water worlds frozen solid and cast adrift, carrying the building blocks of life from one star system to the next in a form of galactic panspermia? Are there objects that are not natural at all? This is the legacy of 3I, Atlas. It is the legacy of all great exploration. We set out to map a familiar coastline and discovered an entirely new continent. The journey to understand this single point of light has become a journey into ourselves, a confrontation with the limits of our knowledge and the boundlessness of our curiosity. It has taken our most cherished certainties about how worlds are built and how the universe works and has gently but firmly set them aside. It has taught us that to truly explore the cosmos, we must be prepared to abandon our assumptions, to listen to the evidence, no matter how strange, and to accept that we are and may always be beginners in a universe of endless surprise. The darkness between the stars is not empty. It is a repository of secrets, a library of cosmic history filled with the messengers of a billion other worlds, each with its own story to tell. We have now for the first time learned to read a single extraordinary word from that library, and as we continue to watch the skies with new surveys and more powerful telescopes coming online, we know that more messengers are on their way. The conversation with the universe has just begun. What it will tell us next is anyone's guess, but we can be certain of one thing: it will be wonderful.